Right now, 100 billion stars are burning. They have burned for billions of years, and they feel permanent. They are not permanent. Stars consume finite reserves of hydrogen fuel, and when that fuel is gone, they die. The universe has a clock, and it is running down. In roughly 100 trillion years, the last new star will ignite. After that, no new stars will ever form again. The stellar furnaces will go cold one by one. The final chapter of active matter in the cosmos will not be an explosion. It will be a ball of frozen iron sitting alone in the void. This is the Black Dwarf, the stellar corpse that will outlast everything else in the universe. No black dwarf has ever been observed. The universe is not yet old enough to have produced one. Everything we know about stellar physics and quantum mechanics tells us they are coming. They will outnumber every star that has ever burned and outlast everything else that has ever existed. In 1997, astrophysicists Fred Adams and Greg Laughlin at the University of Michigan published a paper titled A Dying Universe: The Long-Term Fate and Evolution of Astrophysical Objects. Adams and Laughlin divided the future into 5 eras, each spanning timescales incomprehensibly larger than the previous. To make these scales manageable, they used a logarithmic time measure, the base 10 logarithm of years. On this scale, the universe today, 13.8 billion years old, sits at a value of roughly 10. The primordial era runs from the Big Bang to the first stars, log 0 through log 6. The stelliferous era, the era of stars, spans from log 6 to log 14. We are living in the stelliferous era right now, near its peak. The degenerate era follows, from log 14 to log 40, the age of stellar remnants after all stars have died. The black hole era runs from log 40 to log 100, and the dark era encompasses everything beyond log 100, after the last black holes have evaporated. To understand what black dwarfs are, you need to understand what happens to stars like the Sun. The Sun is a middle-aged main-sequence star, fusing hydrogen into helium in its core. It has been doing this for 4.6 billion years, and has roughly 5 billion years of fuel remaining. When the hydrogen in the Sun's core is exhausted, the core will contract, while the outer layers expand dramatically. The Sun will swell into a red giant, engulfing Mercury and Venus, before shedding its outer layers as a glowing shell of gas, a planetary nebula. What remains at the center will be a white dwarf, roughly the size of Earth, containing roughly the mass of the Sun. White dwarfs are not held up by nuclear fusion or thermal pressure. The matter inside them is in a state called electron degeneracy. In normal matter, electrons orbit individual atomic nuclei with vast empty space between atoms. In a white dwarf, gravity has compressed the matter so completely that electrons are stripped from atoms and form a dense quantum sea. These electrons obey the Pauli exclusion principle. No 2 electrons can occupy the same quantum state simultaneously. This creates electron degeneracy pressure, a quantum resistance to compression that does not depend on temperature. Unlike thermal pressure, electron degeneracy pressure does not diminish as the object cools. A white dwarf can cool to near absolute zero and still not collapse. This quantum stability is what makes the black dwarf possible. A freshly formed white dwarf has a surface temperature of around 100,000 degrees Celsius. It has no internal energy source, no fusion, no reaction of any kind. It can only radiate its stored heat slowly into the void. Astrophysicists have modeled this cooling process in extraordinary detail. Brad Hansen at UCLA has used white dwarf cooling curves as cosmological clocks, measuring the ages of star clusters from the rate at which they fade. The cooling is exquisitely slow. A solar mass white dwarf takes 10 to 15 billion years to cool to roughly 4,000 Kelvin, about the temperature of a dim red ember. To cool to 2,000 Kelvin takes roughly 1 trillion years. To cool below the temperature of the cosmic microwave background, about 2.7 Kelvin, takes approximately 10 quadrillion years. 10 quadrillion years. That is 10 to the power of 16. The universe today is only 10 to the power of 10 years old. We are 1 million times too early for the first black dwarf to exist. Every white dwarf in the observable universe is still an ember, still cooling. The black dwarf is a theoretical certainty the universe has not yet had time to produce. As the stelliferous era winds down, star formation will slow and stop. The gas and dust clouds that birth new stars will be exhausted, consumed by existing stars, or dispersed too thinly to collapse under gravity. The last stars to form will be the smallest and most efficient, red dwarfs. Red dwarfs burn their hydrogen extraordinarily slowly. While the Sun burns for roughly 10 billion years, a red dwarf with 8% of the Sun's mass can burn for up to 10 trillion years. The final red dwarf will gutter out roughly 100 trillion years from now, log 14. After that, the degenerate era begins. The degenerate era universe will be populated by stellar remnants, white dwarfs, neutron stars, and black holes, and by failed stars, brown dwarfs, objects too small to ignite nuclear fusion, slowly cooling in the dark. There will be no light sources, no warmth. The universe will be dark, cold, and vast, populated by remnants drifting enormous distances from one another. Occasionally, two brown dwarfs might collide and merge, and if their combined mass crosses the ignition threshold, a brief, dim star could flare for a few billion years. But these collisions will grow rarer as the universe expands and remnants disperse. By roughly log 20, even this last flicker of stellar activity will have ceased. Meanwhile, gravitational perturbations will slowly strip planets from their dead star systems over billions of years. Eventually, even the stellar remnants themselves will spiral inward toward galactic centers through gravitational radiation, disappearing into central black holes. The degenerate era will erase even the large-scale structure of galaxies. What happens next depends on a question particle physicists have not yet answered. Do protons decay? Grand unified theories of particle physics predict that protons are not stable. A proton will eventually transform into lighter particles, a positron and a pion, in a process called proton decay. The predicted timescale is between 10 to the 33rd and 10 to the 36 years. The Super Kamiokande detector in Japan, 50,000 tons of ultra-pure water buried deep underground, has watched for this decay for decades. No proton decay has ever been observed. If protons do decay, every black dwarf in the degenerate era would slowly dissolve, each decaying proton releasing a tiny pulse of energy that reheats the object from inside. A proton-decaying black dwarf would glow with the warmth of a single light bulb until the last proton decays around log 37. Then it would vanish. Not a collapse, not an explosion, but a quiet disintegration into a diffuse cloud of positrons and photons. But if protons are stable, which current experiments suggest, black dwarfs persist. And on timescales that dwarf even the degenerate era, something extraordinary happens inside them. Even in a cold, dark black dwarf, quantum mechanics does not stop. At the extreme densities inside a black dwarf, a process called Pycnonuclear fusion, pressure-induced nuclear fusion, continues at an infinitesimal rate. Normal stellar fusion requires high temperatures. Nuclei need enough thermal energy to overcome their electromagnetic repulsion and get close enough to fuse. Pycnonuclear fusion is different. At extreme densities, quantum mechanical tunneling allows nuclei to fuse even when the temperature is essentially zero. The nuclei do not overcome the electromagnetic barrier, they tunnel through it. This was first seriously analyzed by Freeman Dyson in his 1979 paper, Time Without End, Physics and Biology in an Open Universe. Adams and Laughlin later refined the calculation with full stellar evolution models. The rate of pycnonuclear fusion is so small it is meaningless on any human or even astronomical timescale. But given enough time, and the deep future has time that defeats all intuition, it accumulates. Iron 56 is the most tightly bound atomic nucleus in existence, the endpoint of all possible fusion reactions. The pycnonuclear reactions inside a black dwarf will gradually transmute lighter nuclei into heavier ones, climbing the periodic table one quantum tunnel at a time. Over a timescale of approximately 10 to the power of 1,500 years, the entire mass of a black dwarf would be converted to iron 56. At that point, it becomes an iron star. Cold, dark, completely inert, a sphere of pure iron, the final resting state of ordinary matter. Meanwhile, black holes, the other long-term survivors, are not eternal either. In 1974, Stephen Hawking at Cambridge showed that quantum effects at the event horizon cause black holes to slowly radiate energy, Hawking radiation. The rate is almost unimaginably small. A solar mass black hole radiates at a temperature of 60 billionths of a Kelvin, but over time, a black hole loses mass and eventually evaporates completely. A solar mass black hole takes approximately 2 times 10 to the 67 years to evaporate. The supermassive black holes at galactic centers, billions of solar masses, take on the order of 10 to the 100 years to evaporate. When the last black hole evaporates, the dark era begins. Nothing remains but a dilute sea of photons, neutrinos, electrons, and positrons, drifting through an expanding void. No structure, no heat, no complexity. The thermodynamic heat death of the universe. Sit with this for a moment. The sun you see every day will become a white dwarf in roughly 7.5 billion years. That white dwarf will cool for quadrillions of years, longer than the universe has existed, many millions of times over. It will eventually become a black dwarf, a cold, dark sphere, drifting through a universe where no stars burn. And then, over 10 to the 1500 years, even that sphere will quietly transmute through pycnonuclear fusion, atom by quantum-tunneled atom, into iron. The universe will not end with a bang. It will end with silence. But here's what I find haunting about this picture. The degenerate era alone, the era of cooling black dwarfs, spans from log 15 to log 37. That is an expanse of time that makes the current age of the universe look like the first microsecond of a human life. For the overwhelming majority of the universe's future, the dominant objects in existence will be black dwarfs. They will vastly outnumber every star that has ever burned. They will outlast every planet, every civilization, every stellar remnant except the largest black holes. We are living in the stelliferous era, the brief, brilliant, anomalously warm moment when the universe is lit by stars. We are not in the typical era of the universe. We are in the unusual one. The vast majority of the universe's timeline is cold and dark. The stellar era, the warm one, is the exception. We are inside the exception. There is a question that follows from this. If the universe's default state is cold and dark, and if we exist in this brief warm window, is that random? Or is warmth and complexity a necessary condition for observers? The anthropic principle holds that we could only exist in an era capable of supporting life, which requires stars. No observer could arise from the dark era's sea of cooling positrons. No mind could form in a universe with no chemistry, no gradients, no free energy. The fact that you can ask the question is itself a product of the timing. You exist in the narrow window where the universe is complex enough to support an observer. Every question you have asked, every moment you have experienced, all of it is happening in this window. Against the backdrop of 10 to the 1500 years of iron silence, this window exists. That is not a small thing. The universe does not owe any era its warmth. The stars are burning now. This is when it happens. The black dwarf era is not a tragedy. It is what comes after a very long story. The story is happening right now, in the light. When the last star goes dark, and the last black dwarf cools, and the last iron sphere drifts alone in the void, it will carry the atoms that were once inside stars. The same atoms that were once inside you. Stars, briefly. Then iron. Then silence.